So this is an ice cube relay. That's how it looks like. That's the ice cube relay, and this is the base. So essentially what an ice cube relay does, or how it works, is you're using low voltage, such as this one. The coils are 24 volts DC, and you can use that low voltage to control voltage as high as 250 volts AC. So the contacts inside this relay, you can see them there. Those contacts are rated at 5 amps, 250 volts AC. A1 and A2 are the coils. Here's A2 and here's A1. You can see the pinout on here. A1 and A2, or numbers 13 and 14, are your coils. So if you put 24 volts positive here and the negative side here, it is going to energize that coil inside there. And when that coil inside there energizes, it's going to switch the state of the contacts. The normally closed side is going to break open, and the normally open side is then going to close. So if you look at the pinout, these numbers over here are your poles. 12, 11, 10, and 9 in parentheses, or 11, 21, 31, and 41 are your poles. And this side over here are your throws. So you have double throws on each pole. 9 to 1 is normally closed. 9 to 5 is normally open, and so forth for the other poles and set of contacts. This particular relay has NEMA and IEC standard on it. That's why it looks kind of confusing. You know, like for example, IEC standard, you might call out 11 is common to 12 and 14, where NEMA standard, you're going to call out 9 to 1 is 9 is common to 1 and 5, and from 9 to 1 is closed, 9 to 5 is open. It's just a standard, but they're literally talking about the same set of contacts and terminals. Same as A1, A2, 13 or 14, you're talking about the coil, that's all. It's just how NEMA likes to name their stuff, and IEC likes to call out their stuff. So if you were to run 120 volts through the normally open side of this contact because you want to control a load when the relay energizes, then you would use 9 to 5, because that is the normally open side. So when the relay energizes, it's going to swing close. So then you just look at your terminal 9. This is terminal 9. You run your 120 hot to this side. That's the COM side. And then you run a wire out on terminal 5. Again, here's terminal 5, 9 to 5. So you look here, here's terminal 5, and you run a wire out this direction to the load, to whatever load you're trying to switch on. And if you're trying to turn a load off when the relay energizes, you would go from 9 to 1. So again, you would run a power wire to 9 on the base, and then you would run a wire from 1 to your load, whatever load you're trying to control. And when the coil on the relay energizes, 9 to 5. 9 to 5 is gonna have continuity, and then 9 to 1 will break continuity and it will shut off that load. The load on terminal 5 will then energize or be on. So that is explaining it in its most simplest form that I can explain. Stay tuned for part 2. I will make a quick video on using the normally open and normally closed contacts to run a load. Stay tuned for part 2. I will make a video on using the normally open and normally closed contacts to run a load. So here's the quick setup that I have. I have the power supply that's going to bring in 24 volts DC from this red wire. It's going to come over. I'm going to have it hooked up to this wire, red wire here, then goes to A1. That's the positive side for the coil, and on the negative side of the coil I have this white wire. It's not hooked up in line yet, but once I touch this to this alligator clip, it's then going to complete the path back to the power supply on the negative side, and the coil should then energize. And once the coil energizes, it will then close the normally open set of contacts of 9 and 5. So here is terminal 9. I have a hot wire running 120 coming to that COM terminal right there, and I have 120 fan motor here wired to terminal 5. So remember, 9 and 5 are normally open sets of contacts. So as soon as this relay energizes, that contact will close, and it will provide continuity or a path for current to flow to the motor, which then allows that motor to start working. So just to show you, I have 120 volts right there on the COM side, and on terminal number 5 there's nothing. But once the relay energizes, 120 will then pass through and be present over here on terminal 5. Alright, so here we go. There it is. Now I have 24 volts to the coil. You can see the light is on. That means that the coil is energized, and our normally open set of contacts are now closed. See, now I have 120 on terminal 9, and if I check terminal 5, here's terminal 5. I'm probing it right now. There's the 120. It has passed through the contacts on this relay. So then now it allows the motor to work. So we tested terminal 9 and 5, which are the normally open side. Now I move the wire from the motor to terminal 1, which is the normally closed side. So 9 to 1, that's the normally closed side. So I now switched it, and we're gonna test to see how that functions. So on the normally closed side, you're always gonna have 120 passing through terminal 9 and terminal 1. Like right now, the motor is on, and if you would check for voltage, you would have 120 at terminal 9, and you would have 120 at terminal 1. That's why the motor is turning. But if we would energize this coil, right now there's no power to the coil, the power supply is off. Let's turn on this power supply. There's our 24 volts. If we would energize this coil, it would then cut off continuity through this relay. Terminals 9 and 1 would have no more continuity, and the motor will stop. So let's check that out. There you go. So right now the coil is energized, and our 120 is cut off to the motor. As soon as we de-energize the coil, it starts back up. That's the normally closed side of the relay.